process called adiabatic process is actually one of the more important ones. Thinking whether I should go to the new page. I think it's probably okay. So adiabatic process. Adiabatic process is a special process where there's no heat flow in or out from the system. So in terms of variables, that means Q equal to exactly 0. Okay, so there's no heat flowing in or out. This is important because in the kind of real life situation, if you may, there's a lot of time where there's very little heat flowing in or out from the substance that we are studying. And that just means the container that you use for that particular substance is very good in terms of insulating heat. For example, nowadays everyone have seen or used, the thermal insulating cup, like the Yeti cup, right? So it can keep the cold water to be cold many hours. It can keep hot water to be hot many hours. Is the kind of the same idea here. It can do that because there's very little or almost zero heat flow between outside and inside the cup. Okay, but ideally Q will be exactly 0, and that's what we call adiabatic process. Okay, so adiabatic process, the calculation is a little bit difficult to do. So I'm not going to go through the proof, but you can, if you want, you can look at any textbook that you can find. You're going to find the derivation in there. But the derivation is not the most important thing for us here. So I'm not going to do that, but I'm going to write down one particular formula here for adiabatic process. So before doing so, let's talk about the PV diagram. Okay, so Q equal to 0, that means delta U equal to Q minus W, and Q will be 0 for adiabatic process. So delta U equal to minus W. Okay, so if you want to change the temperature of the object, you are not allowed to heat it up. You're not allowed to cool it down by bringing it in contact with ice or something like that. The other thing that you can do is to compress or to, expand the gas. That's it. Right? So if you expand the gas, W is positive, right? Gas expansion gives you positive work. That means the gas has to cool down. So that's the minus sign here. Okay, so delta U is minus W. So if W is positive, the gas has to cool down. So delta U must be negative in that case. Okay. On the other hand, if you compress the gas, work is negative, right? Because volume decreases, then the temperature of the gas must increase. Okay, so that's the meaning of this equation here. Adiabatic process is also a process where the line on the PV diagram is not a straight line, so it's also a curved line. Usually we gonna compare adiabatic process with isothermal process, right? So what I'm gonna do is I'm gonna draw two isotherms as a dashed line, one here and another one here. So remember, these two are just the two hyperbola with different temperature. Which one is higher temperature? The one further away is higher. So T2 here and T1 here. Okay, so T2 is larger than T1. Okay, so if you move from anywhere on this isotherm to anywhere on the other isotherm, you reduce the temperature. Okay, so adiabatic process, usually the way to describe it is it's gonna be a little bit steeper than isotherm. For example, if you start from here as the starting point, so P and V diagram, um, isothermal process follow isotherm, so it's gonna be following that hyperbola. But adiabatic is steeper than that. So sometimes it's gonna be something like this. So end up here. Okay? Which makes sense because adiabatic process, temperature is not guaranteed to be constant. Actually, temperature cannot be constant because otherwise you do nothing. Okay? So that's the adiabatic process. So I say it's steeper than isothermal because isothermal is going to be like that, right? So it's steeper compared to the green one. So that's what I mean. Okay, so adiabatic is like that. So the exact um, curve can be described by this equation, which again I will not prove, but you can find the proof anywhere. Okay, so this curve here is the curve described by PV to the power of gamma equal to constant. This is in contrast to the isothermal process. Isothermal process is PV equal to constant. This is isothermal. This is adiabatic. Okay, so this one you understand from our discussion before the break. It's just PV equal to nRT, and N and R and T are all constant, so PV equal to constant. But adiabatic process, T is not constant. Okay, T changes. But somehow, if you do something like this, PV to the gamma is equal to constant. And what is gamma? Well, gamma can be shown to be the ratio of Cp and Cv. Okay, so suddenly these two things appears out of nowhere. So apologize for that. It has to be from formal proof, which again I'm not going to do that because it's going to spend too much time. And what is Cv and Cp? Well, that's exactly what we talked about earlier. Cp is just 5 half R. Cv is 3 half R. Okay, so in a sense, where we okay, we are here. So in a sense, gamma is just a number because Cp is 5 half R, Cv is 3 half R. Then you tidy up the number a little bit. Gamma is just 5/3, like this. Okay, so that means that particular equation PV to the power of gamma equal to constant is just PV to the power of 5/3 equal to constant for adiabatic process. Okay, so for adiabatic process, then you use this formula here. All right. For example, let's take a look at. Well, actually, I just want to copy this so I don't have to redraw. Copy and then paste. Okay, so this is adiabatic process. So let's just put in some numbers so that you know how to use that equation. So let's say we start at the pressure up here, which let's say is 2 atm. So let's say this is in atm. And then the initial volume is, let's say, 1 cubic meter. Okay, and let's say you follow this adiabatic process. Okay, so you end up here. So you end up the place where the volume doubles. Now we want to find out what is the final pressure here. So what is P here? P at point B equal to what? Okay, so in this case, what do you do? Well, it's an adiabatic process, so you need to use PV to the 5/3 equal to constant. Right. So if I label the first point to be A, the second point to be B, then what I need to write down is P at point A, V at point A to the 5/3 power equal to P at point B, V at point B to the 5/3 power, like this. Okay, so remember that it's not the same as isothermal where PV equal to constant. This is adiabatic. All right, so that's the common mistake that I see quite often, that you mix up the formula, right? So the process, the kind of process dictates what formula you use. So in this case, it's adiabatic, so we use this one. All right, so let's just put in the number. Since the unit for pressure, we're going to keep as ATM, so we don't need to change it to Pascal. So PA going to be 2 ATM. VA and VB can be combined together. So I'm going to do it like this. It's going to do VA over VB to the 5/3 power equal to PB. Okay, and then I'm doing this because then I can cancel out the unit for the volume, right? Because otherwise you're going to have the volume to the 5/3 power, which is kind of strange. So it's a lot cleaner to just divide the volume first before you do the exponent. So VA is 1 divided by 2, 5/3, that's going to be equal to PB. So the rest is just, you know, putting in the calculator, which is going to be 0.5 to the 5/3 power times 2 ATM. Right, 0.5 times to the 5/3 multiplied by 2. So that's going to be PA equal to about 0.63 ATM. Okay, so that's how we calculate the pressure at the other point. Okay, so it's PB to the 5/3 power. So the 5/3 power, that's only applied to the volume, okay? So it's not the whole thing to the 5/3 power, because otherwise it's going to be the same as PV equal to constant. All right, so that's another thing that some students, oh, sorry, yeah, PV, thank you. Right, because PA is the initial point. So PB is what we want, 0.63 ATM. Okay, and then if you want to calculate something related to temperature, like what's the temperature at point A, what's the temperature of point B. So once you know pressure and volume at both point A and point B, then you can use PV equal to nRT to calculate the temperature. All right, so this is a very good point to kind of step back and then review the whole thing, because it's quite a lot of information, right? So I'm gonna write the formula which applies to every process, okay? It's the universal formula. So I'm gonna divide my kind of summary table to be in two parts. So the first part is the always true part, always true. Okay, this is the formula that you can always use no matter what kind of process that you're dealing with. So the always true part, first of all, is PV equal to nRT, which is equal to nkBT. This is always true. Okay, this is the formula for the ideal gas law. It's nothing to do what kind of process you are talking about. Okay, this is always true. The other always true is delta U equal to 3 half nr delta T or 3 half big N Kp delta T. This is also always true. Now it might be 0 for some process, but this formula is still true, okay? Because again, this is probably the 8th time I've said this already. Internal energy for gas depends only on the temperature. It doesn't care how you go from one point to another point in the PV diagram. Okay, so as long as you know the change in the temperature, then you can write down delta U. Now the rest depends on what kind of path that we talk about. So the next kind of table I'm gonna write down, I'm gonna call it the path dependent variables. Okay, so we talk about 4 processes. So let's list that down. So we're gonna have isobaric, isochoric, isothermal, and adiabatic. Okay, and maybe I should write the other one, which is the first law of thermodynamics. But I think it should be clear to you that the first law of thermodynamics should always be true. Right. Again, it's just the conservation of energy, right? But anyway, I'm writing this down because normally when you calculate these processes, you want to know one of these 3 variables, right? Sometimes 2 are given, so you calculate the third one. So I can have the column divided by delta U, Q, and then W. Okay, and we can fill in this table. So let's do the obvious thing, which is the definition of the process itself. So what can we say? Isobaric, well, maybe we can skip that for now. Isochoric is volume constant. Volume constant means work is 0. Actually, let me just draw a thin line that divides. So that is clear what we are talking about. Okay, so isochoric W is 0. That's easy. Isothermal, temperature is constant. So delta T is 0, means delta U is 0. So this is 0. Adiabatic process, Q is 0 by definition. So we can write it down like this. Okay, so that's kind of like almost half the work already. Actually missing this line here. Okay, so the rest is just rewriting the equation that we have derived earlier. Okay, delta U is always this, right? It might be 0 again, but it's the same formula all the time. So we can just write 3 half nr delta T, 3 half nr delta T, and 3 half nr delta T for every row in this table, except for the isothermal where it's exactly 0. Okay? And for Q, well, isobaric Q can be expressed in terms of NCP delta T, which is just a shorthand for 5 half and delta T. Okay, that's fine. And then the work done is just P times delta V, right? So remember that's the case for the rectangle area. So it's very easy to calculate the work done, which is just the rectangle formula. For isochoric, V is constant, so it's going to be NCV delta T, so it's going to be 3 half and delta T. Okay. And for isothermal, well, the work done is a little bit messy because it involves the logarithm of V2 over V1. But Q is the same as W, so we can just write W here. Because delta U is 0. Yeah, so it's just applying this formula. And adiabatic is Q equal to 0, so that means W is just minus delta U. Okay, and if you want to be specific, like what exactly is delta T here, then you can use PV to the 5/3 equal to constant to help you with this calculation. Okay, so that's for adiabatic process. All right, so this is kind of the summary of what we have talked about in this lecture and also the second half of last lecture. All right, this is what we're gonna use to talk about actually the even more important thing. Well, the process itself is important, but the process alone does not complete what we call the heat engine because, well, you're gonna see later that a heat engine comprised of many processes. So before we do that, we have to talk about one particular case, which is called a cyclic process. This is nothing new actually, it's just the way we used to describe a process where you end up at the same place. Right. So what it means is that you are moving along this PV diagram. For example, from this point to this point here. So maybe you follow one particular path, I don't know, it may be adiabatic, it may be isothermal, whatever. All right, but you go to here, so point A to point B, and then you want to repeat the whole thing. So if you want to repeat the whole thing, you better go back to the original point. So for example, you might be going back through a different path here, like this. Okay, so this is it. This is what we call a cyclic process. So a cyclic process means that a process where the gas returns to the starting point in the PV diagram. Okay? So why do we talk about this one? Well, because for any engine, you need to be able to repeat the engine many times. Right? So you don't want to just expand the gas and then that's it. That's a very bad thing to have. Right? You want to expand the gas, then you probably compress it so that you can repeat the whole process again. The point of this is that every time you do complete one process, one cycle, right? What we want in the end as a user is to be able to extract work from the gas. Okay, that's the point of what we call the heat engine, right? And you can use the work that you extract from the gas to do whatever you want, to run the car, to produce electricity, to do whatever you want. Okay, so you want to be able to repeat that many times so that if you need more energy, more work from the system, you just run it longer. Okay, so in one particular cycle, you go from A to B here, right? So what happened here? What happened here is that you're gonna have, well, not you, like the gas gonna have to do some work to go from A to B. Following, let me just call this path to be path number 1. And then I will call the upper one to be path number 2. Okay, so going from A to B, then the gas gonna do this much work, right? The area under the curve for path number 1, right? So work from A to B gonna be work from path 1, which is the blue area here. Okay, so just draw the blue area here. And then to go back from B to A, let's say we follow a different path, the upper one, path number 2. Then you also gonna calculate the work done, but now the area under the curve is different. It's the green one here, right? So it's the green one, which due to the coloring, it might not be clear what happened if I use yellow here. Or maybe it's clearer. Well, okay, you get what I'm trying to say. So work from B to A is work number 2. That's the yellow curve, yellow area, which is the whole thing, okay? Which is the whole thing, this whole thing here. Okay, the color is a little bit hard to say what's happening here. So altogether, when you go from A to B and then back to A, right, you need to add the two paths together. So the total work is going to be work from A to B plus work from B to A, which is work from path 1 plus work from path 2, right? But the thing is that work from path 2, that's negative, right? Because the volume of the gas decreases, right? So I should note here there is the negative value for work for path 2. Okay, so when you add them, actually you are subtracting the two numbers together. So in the end, what you are left is the area enclosed by that curve, which unfortunately is the yellow area, but actually this is what we want. Okay, so it's just this area enclosed by the path. That's the total work done in one cycle. Okay, and this case, it should be clear to you. If not, try to convince yourself that the total area for one cycle, which is this enclosed by this path, that's negative. Okay, because going back gives you more negative number for work. If you want to have positive work done by the gas for one cycle, then the direction of the arrow on the diagram should be reversed. Okay, so to summarize the point that I'm talking just now, let's have two PV diagrams side by side. So PV and then PV. Okay, so in other words, we have what we call the heat engine. I'm gonna say again in a few minutes what exactly we mean by heat engine. Is gas which is operate in cyclic order, cyclic process. So it has to go in a closed loop like this. But you have a freedom of running it backwards. So the same path, I'm trying to make it the same. but you can run it this way, right? So this way, the direction where you traverse along the curve here, you can call it counterclockwise or something, right? Because it's going, like backward, and you can call this clockwise, going along this, right? So if you go in the counterclockwise, then every cycle, meaning that every time you complete one cycle, you back to the original point. The net work done by the gas, which is the area enclosed here, that's going to be negative. So negative work per cycle. But if you do it in a clockwise manner, so you go here and then up here and then you go down like this, right? Then the area under the curve might be the same, but the sign is reversed. So it's positive work per cycle. And all of this can be justified by the same kind of calculation that we did up here, right? So the cyclic process, you just divide it into going one way and then going back and then subtracting or adding the work done, right? But in any case, the conclusion is that for a cyclic process, the one that you have a closed path, and it can be any path, it doesn't have to look like, I don't know what this looks like, beans or something, right? It can be a circle, it can be a rectangle, it can be anything as long as it's closed, then we call it a cyclic process, right? So, yes, the blue area is actually, let me draw it this way. So the blue area is just the lower part. So let me draw it this way, maybe it's clearer. That's the blue area. And the yellow area is the one that we go back. So that's the whole thing. And when you subtract them, you are left with just the center part, and that's the green area. Right. So maybe I shouldn't draw too much here because it's kind of confusing. So maybe this is clearer. Is this okay? Okay. Right, so when you subtract the two, then you are left with just the enclosed area here. Okay, so the enclosed area tell you how much work you get per cycle, and whether it's positive or negative, it depends on which way you are going around this loop. Okay, so we have about 10 minutes left, so let me introduce to another concept which we're going to develop more for the next lecture, and that's the concept of what we call heat engine. So heat engine. So this is kind of like the point of all this discussion. Like, why do we talk about this? It sounds so abstract, like gas expanding, gas, you know, being compressed. What do we use it? How do we use it in real world? We use it in building what we call a heat engine. Okay, what is a heat engine? Heat engine is something that we can extract the work from, and we can use that work to do anything we want. Right? So the point of heat engine is trying to extract work from dynamical, or not dynamical, thermodynamical, I should say from thermodynamical, not just one process, but multiple processes, okay, to extract work so that we can use work to do what we want, to run the car, to fly an airplane, okay, to operate the machine, okay, to produce electricity, anything that require work and you don't want to do that work yourself, okay, you need to have some kind of engine to do that for you. Okay, and heat engine is one particular engine that we can extract work from this expansion of gas, contraction of gas. Okay, another type of engine is might not be heat engine. For example, you might have like electric motor. That's not a heat engine because you just get work from electrical you know power, electrical energy, right? So heat engine, I see that in the next maybe 10 years or 20 years will become less and less prevalent in our society because it's just not as efficient compared to like other ways of doing. But it's nowadays like still it's gonna be one of the most important way of you know doing work without us doing it ourselves. Okay, but the term heat engine also talks about another specific requirement is that the engine, which is the heat engine, has to operate between what we call two heat baths. So this bath is like bathroom bath, right? It's two heat bath with fixed temperature TH, which stands for high temperature, and T low temperature. Okay, so the only thing that this line means is that if you want to extract work from gas through thermodynamical process, then you have to have somewhere to dump the heat, and you have to have somewhere to put in the heat, and that's what we mean by this two heat bath. Right? So the high temperature is the part where you can extract heat from, and then the low temperature is where you can dump away heat from your system. Right? So the example is when you talk about the air conditioner. That might not be the best example, but that's probably the one that we use to the most, right? So if you talk about the air conditioner, the point of this is that you have your room, okay, and then you have an AC here in the room, right? And then what is this doing? Well, it has the outside compressor, which hopefully you know that any AC require compressor to work. So this is the AC unit. This is the compressor. So what's happening here? Well, the role of the AC, the air conditioner, is to take out heat from inside the room. Okay. So I can draw the arrow like this, and then dump it out to the outside, like that. Okay. So the two temperature that we are operating this heat engine, which is the air conditioner, is the outside temperature TH and the inside temperature TL. Right. So it's operating between these two temperature, and the role of this AC is to take out heat from the low temperature and then dump it into the high temperature like this. Right. If you are born or live or study in not in Thailand but maybe in the Scandinavia where it's cold all the time, this is not what you want. You don't want the air conditioner because it's already cold enough, right? So you have it the other way around, right? You want to put in the heat into the room, right? But still, the heat engine, which in that case might be a heater, operates between two temperature, which is the inside temperature in the room and the outside temperature, right? So those two temperature are what we call heat bath because you can just dump any amount of heat into outside or inside, and we assume that the temperature outside will not change. So that's what we mean by heat bath. Heat bath is just, it's just the heat reservoir. It's just something which is so big that you can take any amount of heat that you want, and the temperature of that thing will not change. For example, the outside temperature, right? No matter how much heat you get from the outside is not going to get any colder, because I mean, what we are talking about here is the air of the whole country, right? That's a lot. But anyway, because of this, every time we want to draw a diagram for a heat engine, we're gonna draw it in this way. So we're gonna have heat bath, which is high temperature, denoted by something like this. And then we're gonna have the lower temperature side, which is TL, low temperature. And we have the engine in between, the heat engine in between. And the way it works is this. The engine will try to extract heat from the hot side, and then it will try to convert this extracted heat into useful work that we can use. So essentially W is what we want. And because there's a limitation on how efficient this engine can be, you cannot convert all the heat into work. You need to throw away some kind of heat into the low side like this. Okay, so this is a typical heat engine, and you can run it in backward. For example, you can put in work to move the heat from the low side to the high side. So in this case, you put in work, and what you do is you extract heat from the low side to the high side like this. Okay, so these two pictures are probably the most universal that we gonna talk about in the next lecture, right? So you can extract heat from the hot side, you get some work done, or you can put in work to move the heat in the other direction. Okay, so in general, we're gonna call this a heat engine. And the bottom one is what we call a refrigerator, or the air conditioner is one of them. Okay, so it's just a heat engine run in the backward direction. Okay, but anyway, we're gonna talk about this on Wednesday. Okay, so that's all I'm gonna talk to you for today, and I'll see you on Wednesday. So take care, guys, and then I'll see you later.